Okay, so what we have here is we have two boxes of mass A and B. Well, so two boxes, A and B, and obviously has a mass of A and B has a mass of B. And we have 80 newtons is pulling up on A, the box A. And we have some tension between A and B with some like massless or almost massless rope. And this thing is falling down. It fell down 12 meters from rest. From rest, it fell 12 meters in 4 seconds. And so what I'd like to know is what is the mass of A and B given those values. Now, like in previous videos, you could just use kinematics formulas like the one above and solve it, and that's fine. I like to approach these problems from a different angle, using like graphs and maybe like and calculus and or geometry, trigonometry, algebra, etc. And so that's what we're going to do. Instead of solving these using traditional kinematic formulas, I'm just going to solve them, my way, which is a little bit different. But I find my way a bit more intuitive, to be honest. Okay, so what I would like to do first is I would like to figure out how fast or what is the acceleration of these boxes as they go down. Great, so let's do that. So as you can see here, I already wrote my the velocity in y versus time. This is a graph. And the area under the curve is 12 because the boxes move 12 meters in 4 seconds. It should say 4. Yeah. And this is the velocity. So it started out 0 meters per second, and it went down to v meters per second. I don't know what that is. And so what I want to do is I want to figure out what is this velocity down here at the bottom. What is this? And then from there, I need to figure out the acceleration. Okay, so let's do that. So you may remember that using some basic trigonometry, the area of a triangle, and you can see here, this is a triangle, is equal to 1/2 times the base times the height. The area, of course, is 12 meters. Half is half. Base is base. Height, the base is 4. The base is 4. Height. And so half of 4 is 2, and then 12 divided by 2 is 6, so that means 6 is equal to the height, and the height here represents the velocity. Great. And we also know that acceleration is equal to change in velocity over change in time. The velocity changed 6 meters per second over 4 seconds, which is 1.5 meters per second squared. So this is a negative 1.5 meters per second squared acceleration downward, because it's going down, right? These boxes are going down. Even though there is a force on the top, they're still going down negative 1.5 meters per second squared. Obviously, without the force at the top, it would be going down a lot faster, right? How fast would it be going? Well, it would be going gravity. Gravity is what? It would be pulling it down at negative 9.88 meters per second squared. So the fact that it's only going negative 1.5 means it's not going. It could be going a lot faster, right? It could be going a lot faster. Okay, great. So now I know it's acceleration, the acceleration of this system. So now let's use Newton's second formula, which says the sum of the forces, and we'll do y, is equal to mass times the acceleration in y. And remember, the forces are a vector. Y is also a vector, so we make sure that everything lines up. So the forces in y have to equal the acceleration in y. So let's do box A first. Box A. It's okay. Well, so if I make a diagram like this, let's make it over here. Okay? This is for A. So two things one thing's is pulling up, and that's 80 newtons. Okay, and then that's part of the problem. And then what's pulling down? Well, the tension in the string, which was 36 newtons. Okay, and also the weight of A. And what is that? Well, that's just 9.8 times the mass of A, MA, or mass of A. Okay? So those are all the forces acting on box A. Okay, so let's do that, where it says sum of the forces in Y. Okay, let's do the sum of the forces. So that's 80 minus, so 80 is going up, and then we have minus 36 minus 9.8 MA. So the 36 is the tension, and then the negative 9.8 MA, that is the weight. And that equals the mass, which I don't know. We'll call it MA. We'll just obviously make sure everything is the same. Times the acceleration in Y. Oh, we know the acceleration in Y. That's negative 1.5 because we just did that. So let's go back here and say, we'll say negative 1.5 MA. Great. So now we all have to do just solve for MA. So 80 minus 36 is 44. Sorry about that. And then we'll move the MA, so we'll say plus 9.8, we'll do plus 9.8 on both sides, and that'll give us a plus 8.3 MA, and now we all have to do is divide by 8.3. Get rid of this, get rid of that. And then so the mass of A is equal to 44 divided by 8.3, or 5.30. 5.30 kilograms. Okay, let's color this. Okay, that looks pretty cool. Now let's do B. So the sum of the forces in Y equals the mass. Here we're actually looking for the mass of B equals A in the Y direction. Okay, so let's do a diagram of B as well too. So this is B. Something is going up, something's going down. Okay. So what's pulling up on B? So let's look at B. What's pulling up on it? Just the tension is. Just the tension. T is equal to 36 newtons, right? What's pulling down on B? It's weight, which is 9.8 times the mass of B. Okay? So the sum of the forces is 36 minus 9.8 mass of B is equal to, mass of B, sorry, that's times that. Negative 1.5, which is my acceleration of B, times the mass of B. Mass of B, great. So all we have to do is just add 9.8 MB plus 9.8 MB, and then we have 36 equals 8.3 MB, that's mass of B, of course. Divide by 8.3, boom, and so we have 4.33. 4.33 equals the mass of B. Okay, there's that. Is that right? 5.30, 4.33. And so if you look right here, whoops, go back. 5.30, 4.33, 4.34. Okay, so you can see we got the same answer, but we didn't have to use any kinematics formulas. We just sort of used this graph. Like I said, I tend to like these velocity versus time, acceleration versus time, position versus time graphs. Using some calculus. In this case here, we just used some trigonometry, and then using Newton's second formula. The sum of the forces in whatever direction is equal to mass times acceleration in that direction, and then some of these force diagrams. Okay, I find this way, like I said, more approachable than just raw kinematic equations. Just to show this, there's another way you could have solved this. You could have said you could have used A and B as an entire block, and so you could have said the whole system here, maybe call it blocks. All the blocks. Okay, and so what goes up, it'd be 80, and then what goes down, it would be mass A plus mass, plus the mass of B times the acceleration in y. Okay. You could have done that. So meaning you could have nulled out the internal forces. So this internal force, this tension, you could have like ignored it because it's internal, and you could have like just like put a whole box around it, and so 80 would have been going up, the force going up, and then mass A plus mass B times the acceleration in y. So you see, that's a third way of solving this problem as well too. Okay, is just kind of ignore the internal forces and consider the whole thing one system, right? Like consider the whole thing one system, and like a black box, and then you have something pulling up, the 80 newtons, and then something pulling down, which is the weight of what? Both A and B. Okay, so that's just another way you could have solved this problem, or another equation. Okay, all right, that's it.